All right, so good morning, everyone, and thanks for joining the session, and thanks for inviting me. My name is Maiwa Amal, and I'm a solutions architect with AWS. First, a bit about myself. I've been with AWS, just shy over a year. Prior to that, I've worked as a solutions architect for the last 10 years. With organizations like Clicatel, Vodacom, and BCX. Prior to that, I worked as a consultant with KPMG, and prior to that, I was a network engineer with a service provider. So I would say I've been in the tech industry for the last 13, 14 years thereabout. So the session today would be on EKS, but I would just want to get a sense from the audience how many of us are familiar with containers before I go into how many of us are familiar with Kubernetes.
I'm familiar with Docker, container, and a little bit Kubernetes also.
Okay. Anybody else? I just want to get a sense of where everyone is, relative to containers and Kubernetes.
I think enough to is familiar with Docker. Okay. Is he watching on the chat?
Okay, so you need to let me know because I can't see what's on the chat because I'm in full screen.
Okay.
Yeah. So I appreciate if you just help call out the chat. If there's anybody trying to get my attention on the chat,
okay,
just let me know because I can't see the chat.
Okay.
I'm familiar with Docker and Kubernetes. There is someone named Zinon who is also familiar with Docker. Everyone, if you have any background on DevOps, on Docker or Kubernetes, please let us know in the chat.
Okay, all right, that's fine. So I would run with the assumption that everybody is pretty familiar with containers. So that's a good start. So this is an introductory session to EKS. EKS is Elastic Kubernetes Service from AWS. So we will just go straight into it. So a quick run through, we would be introducing Kubernetes generally. Just as a recap for those who already know what Kubernetes is, but for those who don't know exactly what it is, maybe this would be a sort of insight into it, and then we will go into how Amazon deploys Kubernetes, and then which is what EKS is, and then we will talk a bit more about the core concepts of Kubernetes. So this is an introductory session. I believe that there might be subsequent sessions where we go a bit deeper into EKS, but this would just be touching EKS from a very introductory standpoint. All right, so what exactly is Kubernetes? So for those of us who are familiar with containers, you know that containers help you to run your workloads, and they make it possible for you to run them on virtually any infrastructure. So all the libraries, the binaries that your application needs to run, you can package them into what is called a container image and basically ship that, and run them on different infrastructure, different operating systems in some cases, So basically, that's what containers help you to do. Now, the more containers you're running in an environment, that can easily scale up so much because of the immense benefits you get from containers. You can easily scale that up and you find that you're running several thousands of containers in an environment. Now, that's where, and managing that can become such a bottleneck, and that's exactly where Kubernetes comes in. So in simple terms, Kubernetes is like a portable, extensible, open source platform that helps you manage containerized workloads. It provides you essentially with a framework to run distributed container systems resiliently. Kubernetes also helps you manage the infrastructure from a scaling standpoint failover for your application, and also provides you what we call deployment patterns to be able to manage your container real estate. So essentially, in simple terms, Kubernetes is a container orchestrator. So this typically is what the Kubernetes architecture looks like. So you would see that you have two sets in a sense. You can see to the left is what we call the control plane, and to the right is what we call the data plane. So essentially, you run your actual applications within the data plane, which can contain from one to multiple physical nodes or servers. Your control plane also runs on servers, right? But it basically controls the rest of what we call a cluster. We will go into a bit more detail around what these are. But I will just try to quickly explain what some of these terms we see on the screen are. So I've already spoken about the fact that you have what we call the control plane. The nodes in the control plane are called master nodes, and the nodes in the data plane are called worker nodes. Now, a very critical component of the Kubernetes infrastructure is what is called the Kubernetes API server. So essentially, it's a part of the control plane that exposes the Kubernetes API. Essentially, that's what all of the other components essentially interact with. That's like the entry point into Kubernetes in a sense. The API server. So you can think of it as the front end of the Kubernetes control plane. Then somewhere there you have what is called etcd. Etcd is what I would call it a key value store, and it's essentially used for storing the state of your Kubernetes cluster. So basically, there are a lot of things going on in the Kubernetes cluster, but that's where the state of the cluster, the exact state of the cluster per time, that's where you find it stored. So think about it as like storage, or like the database for your cluster. Then we also have the scheduler, this one right here. Essentially, it's a part of the control plane that watches for what you call pods. So I will speak about what pods are subsequently, but essentially, schedulers help you create instances of your containers within the nodes. So imagine you're trying to run a container, right? When you give the command to deploy it, the scheduler is the one that listens through the API server and then actually schedules the containers on one of these nodes. So within the Kubernetes world, containers run within what is called a pod. So that's like the smallest unit of deployment within Kubernetes. I will touch a bit more on that. Then we have the concept of the controller manager. So basically it controls processes, like you have a concept of what is called controllers. Controllers basically help you to get things done within Kubernetes, essentially, and the controller manager manages a set of such controllers, from the control plane standpoint. So controllers would include stuff like what we call a node controller, which is what keeps track of the state of your worker nodes. So it notices when a worker node is down, and it's able to replace it, essentially. So basically everything you should see within the control plane is trying to keep tabs on your node. Like I said, it's an orchestrator. So it's trying to help you achieve things you would have had to do on your own naturally, because if you're running containers within an environment that you control, you're the one keeping tabs of, okay, are my nodes up, are my nodes down? And if they are down, you need to manually go and bring it up. But Kubernetes is that orchestrator that helps you manage all of that. So these are the processes that help you do that. So essentially that's like what the controller manager does. And there are a couple of controllers. I'm just giving an example of the node controller, that checks on the pods, on the nodes, and then helps you replace them, depending on what the environment is. We also have the concept, when we now move to the data plane, we have the concept of the kubelet. essentially, the kubelet is like a Kubernetes agent running on those nodes. It essentially communicates with the API server. It monitors the state of your pods or your containers within the worker nodes that it is, and you have the kubelet run on every node that is within that cluster. It's essentially your gateway, or from the node to the control plane. The kube proxy is a network proxy essentially that runs on each node as well. It helps you maintain network rules, and basically is what helps you communicate with other pods or other nodes within the cluster. And then finally, even though it's not shown within the diagram, the third component that runs on the data plane nodes is what is called the container runtime. So essentially, that's what launches the containers on the node. So essentially, think about it as you give an instruction to the API server. The scheduler then determines where that pod or container should run, right? And it speaks essentially to the kubelet. Then the kubelet then contacts the container runtime, and the container runtime then runs that container or the image of the container on the node. All right, so we'll move to the next slide. So I would appreciate if you have questions, just let me know. I would try to keep my answers as short as possible so that we don't run out of time. But I think it would be good that you ask questions just so that you don't forget the question, because I was initially thinking maybe I should wait till the end of the presentation, but I'm thinking that it might be helpful if we can answer the questions right on that slide. So please feel free to stop me if you have questions. So Kubernetes has a couple of concepts, which I'll quickly touch on really quick. So like I said, a pod is the smallest deployable unit within Kubernetes. So you can think about a pod as essentially a container, even though in reality you can run multiple containers within a pod. But for the purpose best practice suggests that you should run one container per pod because it's the smallest deployable unit of Kubernetes. So Kubernetes is controlling pods, and it assigns the pod an IP address and all that kind of thing. So if you need to know what you're doing if you're going to run more than one container within a pod. But essentially, the recommendation is if you must do that, then it must be something very closely related to the application that is running within the pod, because you can only control at the minimal level a pod. Kubernetes doesn't have insight into the fact that there are multiple containers running within that pod, if that makes sense. We have the concept of what is called a daemon set. Essentially, it helps you to run a copy of a pod on every node in your cluster. So essentially, think about it as you want to deploy, say, like observability in your cluster. You want to run like a monitoring agent on every node. That's where a daemon set would come in. And a daemon set ensures that even if a new node comes into that cluster, so maybe you are scaling up and a new node is deployed into that cluster, the daemon set would detect that a new node has come in and it will deploy that pod there. So that's what a daemon set helps you achieve. A deployment is your way of telling Kubernetes exactly what you want to do. So think about it as like a declarative statement. So with a deployment, you essentially tell Kubernetes, this is what I want to achieve. And then Kubernetes goes about to figure it out. So think about it this way. You want to run an application and you want it to have multiple you want it to run in high availability, for example, and you want to have multiple pods, and let's say you want to have three pods, you just basically configure what is called a manifest file, in what is called a deployment, and then you basically communicate to the API server, and it then goes ahead to do that, what you want it to do exactly. So deployment is how you're able to do that, essentially. So you basically declare a desired state, and Kubernetes helps you achieve that. Now, a replica set basically helps you maintain a defined set of pods. within your cluster. So like I said before, replica sets can work within a deployment. So basically you're declaring to Kubernetes, I want to at every given time have at least 3 pods, at least 5 pods, at least 10 pods running this application. A replica set is what helps you achieve that. So even if one of the pods goes down for whatever reason, a replica set would ensure that that declared number of pods that you mentioned, it would help you spin up a new one. That's what a pod does. Then a job essentially helps you to deploy pods and allow them to achieve a particular purpose. So think about it as, you want to run like a cron job. You want to probably run a backup, or you want to export something from your cluster, and you want it to run on, you want to deploy pods to achieve a specific purpose. That's where a job essentially comes into play. So the pods that are deployed with a job are just going to run for the duration that they need to run for. So if it's a cron job, for example, that you want to run, if it's like a backup you want to do, if it's you just want to export something, for example, and maybe you want it to come up at a particular time, that's how you achieve that with a job. And as soon as it is done, the job would terminate those pods. I hope that makes sense. A service essentially helps you to give like a predictable IP address to your pod. So think about it. Pods, like I said earlier, they have IP addresses. Kubernetes essentially gives them an IP address, but the pods can go up, can go down at any time, and a new pod would come up to replace it, and that pod will have a new IP address. Now, so think about, say you have like a 3-tier architecture, you have a front end, back end, running within Kubernetes. And for the front end, you have like 3 or 4 pods that are essentially running as your front end, and they all have their different IP addresses. Now, a service helps you expose those 4 pods with one single IP address. So in a sense, you can think about it as a load balancer in a sense. But essentially what it helps you achieve is that you are able to reach those set of pods through a particular IP address that will remain consistent for the lifetime of your cluster. Then we have the concept of labels. A label basically help you to attach a name or a label essentially to your Kubernetes resources. Kubernetes kubectl is your command line. How you're able to interact with Kubernetes, and then namespace helps you to logically group your resources within Kubernetes. So let's jump straight into EKS. So EKS is a managed service that helps you run Kubernetes on AWS without needing to install, operate, and maintain your own Kubernetes control plane or nodes. So essentially, think about EKS like you would think about RDS. I know how many of you are familiar with RDS. Essentially RDS is a managed database service from like AWS, and it helps you deploy traditional database services, but in an easier to manage form. So EKS is basically doing that for you. So there's Kubernetes, which is an open source tool for orchestrating containers. But then with EKS, we then simplify that process for you. And we'll be seeing how we do that, when we look at the architecture. So let me move straight to the architecture in that case. So this essentially is what Kubernetes EKS looks like. So you will see that there are a couple of concepts. I'm sure most of you are familiar with what we call VPCs within AWS, correct? Hello?
Yes, we will hear you.
Okay, awesome. So essentially, this is like a very high level view of what EKS is. So you have what we run within the AWS cloud. That's typically where your control plane would run. You don't have a view into those nodes that are running your control plane. It's only the data plane that you have control in, and that would typically run within a VPC that you have control over. That's essentially what the slide is showing. But then this is pretty much a deeper view of what that looks like. Now, from this basically shows you the control plane. So what we have on the right in this diagram, is basically what we are trying to expand on in this. So you will see that at a minimum, the API server, which we spoke about in the first set of 2 slides, essentially we run that across multiple availability zones. At a minimum, you would run that across 2 availability zones. This is EKS now. EKS will run at least 2 instances of the API server for you. Now, part of the beauty about this too is EKS would help you scale up those resources if need be. That's part of the managed service that we offer. Then you have the etcd, which I spoke about earlier, which is essentially like the key value store for the state of your Kubernetes cluster. You see that runs across at least 3 availability zones, and EKS helps you, with that scaling. So you essentially don't have to worry about the control plane at all. And because of how this is deployed, we're able to guarantee some SLAs. This is an SLA service. We can provide SLAs for this service, which is what is showing here. It supports that. Like I said, you also have the ability to automatically scale and resize as may be required. This slide essentially is speaking to the runtimes that are available within Kubernetes. So this now is speaking to how we run the data plane. So we have what is called the managed node groups and the self-managed node groups, and we have Fargate. I would be speaking to that in the next slide. Yeah. So essentially, with self-managed node groups, this speaks to the fact that you as a customer, you are managing the data plane nodes yourself. Like we said before, the data plane nodes will basically run within your own customer managed VPC in AWS. But that only works when you're running either the self-managed node groups or the managed node groups. Now, what the key difference is that with self-managed node groups, you have control over that. The AMIs that are running within the nodes or the instances, you determine that. You scale them up, on your own. If you want them to sit within an auto-scaling group, you're responsible for doing that. The managed node groups, on the other hand, is provisioned by EKS in your VPC. And it is recommended that you run EKS optimized AMIs with managed node groups, because that's where you sort of see the benefits, doing managed node groups. Because from an upgrade standpoint, take for example, there are new enhancements to Kubernetes. AWS would inform you that, there's a new AMI available for your cluster, and if you want to upgrade, EKS will help you do that seamlessly. So essentially what it does is it deploys those nodes automatically within auto-scaling groups, and it manages that for you. So if you want to upgrade, it will spin up newer instances and then gradually upgrade your nodes in your cluster and then bring them down as, a new instance is provisioned to replace it. So all of that happens seamlessly. Your application is still available, but then you are able to upgrade the AMIs running within that cluster seamlessly. That's one of the major advantages of managed node groups. Now, what we just show down there is that there are a variant of options that you can run with either the self-managed node groups or managed node groups from an EC2 standpoint. And managed node groups and self-managed node groups are also supported on AWS Outpost and local zones. Now, like I said, one of the benefits of managed node groups, you derive those benefits essentially when you're running like EKS optimized AMIs, but it doesn't mean that you can't still run your own AMIs, right? So you can run the AMIs that you want to, but then even if you're running managed node groups and you bring your own AMIs, then you're also responsible for patching those. And essentially when you need to. But we also have a sort of an OS called BottleRocket. I don't know if anybody here is familiar with BottleRocket. But essentially, BottleRocket is a Linux-based open source OS that is purpose-built by AWS for running containers on virtual machines. It's very lightweight, and it's built purposefully for EKS and for running containers. So one of the beauties about running like BottleRocket AMIs, for example, is that because of how lightweight it is, the surface area for exploitation from vulnerabilities is significantly reduced. So we will then move very quickly into the last runtime option for EKS. We've spoken about the self-managed node groups. We've spoken about the managed node groups. Now, this is the third option, which is called Fargate. So essentially with Fargate, AWS is running and managing the control plane for you end to end. You don't have, when you go to your EC2 dashboard, you wouldn't see any nodes running there because they are managed essentially by AWS and you don't do anything. So AWS spins them up, scales them up, basically manages that end-to-end process for you. So I'll stop at this point. I don't know if there are questions, but okay, I would before the question, you also need to pay attention into some of the caveats with Fargate. Like you can see to the right there, certain considerations like that of things you can't do, like you can't run daemon sets, for example, with Fargate. With Fargate, you basically specify the compute resources that you require. So from maybe CPU and RAM, and Fargate goes ahead to deploy that for you. But unlike self-managed node groups and managed node groups where you can run multiple pods on the deployed instances, with Fargate, every pod runs within its own kernel, essentially. So I just thought to mention some of those considerations. So at this point, I will stop to hear if there are questions or if it's okay for me to continue.
I have a question, please.
All right, go ahead.
On AWS Fargate, when I use it, did my workload been isolated from other customer workloads?
Sorry, does your workload, is it isolated from what?
Well, isolated from other customer workloads.
Yes, definitely. So like I said, when you run Fargate, you are your pod essentially is the only thing running within the kernel that is provided for you. So Fargate will deploy, you specify, I need 2 gig RAM or whatever, whatever that is. Fargate deploys one pod, to it. I don't know if that makes sense.
Okay.
Yeah, so essentially it's only that pod that's going to run within that kernel.
Okay, makes sense for me.
Yes.
I have also a question on managed node group.
Okay.
If I use EKS managed node group, will AWS automatically upgrade my Kubernetes version?
No. So when you use managed node groups, AWS would let you know when there is a new version of the AMI that you're running, for example. So AWS will let you know, or EKS in this case will let you know, and then you can then give the instruction that EKS should help you upgrade that. And EKS will then do that for you on your behalf. But EKS doesn't do that without your instruction. It informs you, and then you then give it the authorization to go ahead and upgrade your nodes. Does that make sense?
Yes, makes sense. Okay, thanks.
All right, so moving quickly to Kubernetes ingress and the load balancer controller. So we had spoken about the service objects earlier, and we said a service was a way to abstract an application running on a set of pods. Essentially, the service would expose those set of pods and give them an IP address. Now, with ingress, Ingress is the way you are able to expose HTTP and HTTPS routes from outside the cluster to services within the cluster. So traffic routing, for example, is controlled by rules that you define in what is called an ingress resource. Now, if you look at this diagram here, like I had said earlier, so you have a couple of pods. So think about these pods running a set of applications, right? Now you expose that application via a service. So anytime you want to speak, you want to make a call to that application, instead of calling, you don't need to be aware of the individual pods that are hosting the application. You just need to be aware of this service. So imagine this is a front-end service. You can call this a front-end service. Once you call the front-end service, essentially you are calling any one of these pods. So now you have a couple of services running in your cluster, and ingress is your way of exposing these services to the outside world. So it is via the ingress that you would be able to type HTTP XYZ. Via the ingress, you are able to expose your application essentially via what you call it, load balancers, either provided by AWS or even third-party load balancers like Nginx, F5, HA proxy, and the likes. So essentially, this is a very high-level overview of what the ingress does. So think about it as you want external traffic into your cluster. Ingress helps you to achieve that. Now, the way it's able to do that is through what is called the from an AWS standpoint, we have the AWS load balancer controller. So within EKS, for example, it's the recommendation, right, that you should run or you should leverage the AWS load balancer controller to expose your workloads running in EKS, so that external parties, if you want to now like maybe map it to your domain name, EKS will help you deploy this load balancer controller within your cluster, and that load balancer controller speaks to the API that would help you create a load balancer. So AWS load balancer controller can help you create either a network load balancer or an application load balancer, essentially. And the way load balancers work in AWS, you get a domain name, right, or an endpoint, a DNS endpoint, which you can then CNAME, for example, to your own DNS entry. So if you have like say abc.com, you can then map abc.com to the DNS endpoint that ALB provides for you, and then you can expose that to your customers. I hope that makes sense. Any questions here? Okay, I assume there are no questions.
Sorry, I have a question.
Sure.
On the pods and services.
Okay.
Can I have a dedicated IP range for my services and a dedicated one for my pods?
So you can have a dedicated IP range for your cluster, right?
Okay.
Yeah, you can have a dedicated IP range for the cluster where these IP addresses will be selected from. Okay. What the service would help you do is that that if you say you have an application, if you put the pods behind that service, right, that service would always maintain that IP address.
Yes.
Yeah, exactly. So you can then create a mapping table somewhere. This is the IP address for this, and all that kind of stuff. But basically, you can define the IP address for the cluster. Essentially, most of all these, the IP addressing within the cluster usually is private IP addressing, by the way. When you then want to expose to the internet and all of that is where you then bring in an ingress. But within the cluster, your services, your pods, they basically are running private IP addresses. And you can specify what that range is, during cluster creation.
Okay, if I understand very well, the IP range will be shared by every pod and service. I asked that because I asked that because on GKA, there is a pattern to have dedicated IP range that your service Kubernetes service will use, and a dedicated one for your pod. There is no something like that on EKS.
So this is more a Kubernetes feature than EKS essentially. But I'm trying to understand why you want a dedicated range of IP addresses for your service and a dedicated set of IP addresses for your pod. I'm trying to get the concept why you want that.
Why? Because sometimes I need to set some firewall rule and say that, by example, if my request come from the IP range of Kubernetes service, I should accept it. So I can allow some of my pods to access some dedicated service behind a firewall.
Okay, fair enough. But I would also think that one way you can do that is since you have those pods accessible through a service, right?
Yeah.
You don't necessarily even need to have any clue what the pod IPs are. You know that as long as those pods can access the service and the service IP address is static, it doesn't change. So that's really the IP address that matters. Once you can define that through a firewall rule for the service, then you know that you can essentially reach the pods. So that's another way to think about it.
Okay.
Yeah.
Thanks.
So we go into how you scale. One of the things we had said before is as an orchestrator, Kubernetes helps you to manage scaling. Now, so how exactly is that done? So there are essentially 3 default ways of doing that, and this is traditional to Kubernetes now, right? Not even EKS. So you have what is called the horizontal pod autoscaling, HPA, vertical pod autoscaling, and the last one is cluster autoscaler. But I'll just touch you very quickly on the first 2. So with horizontal pod autoscaling, think about it as you have, say, when you created your application initially via deployment, you said, I want to run 2 pods or 3 pods, for example, right? But when traffic starts to scale and there's more traffic coming into your cluster, you want to be able to scale from 2 or 3 pods to maybe 5 or 6. That's what horizontal pod autoscaling helps you to do. So it essentially works like autoscaling in AWS in a sense, right? But this time from a pod level. Now with vertical pod autoscaling, what it does for you is, I didn't mention earlier, but with pods, you can specify what we call request and limit. So take for example, you specify a pod and then you say, I don't want this pod to use more than XYZ worth of CPU. I don't want this pod to, you tell it, the request basically specifies at every given time, guarantee that this pod has this amount of CPU, has this amount of RAM. But then the limit then specifies that, if that pod needs to get, it can also use up CPU up to this limit. It can use up RAM up to this limit. So that's what that does. Now, in a scenario where you then find out that the traffic patterns coming in, the CPU that you specified or the RAM you specified, it needs more than that. Vertical pod autoscaling can help you do that. Basically vertically scale that pod. So that's essentially the difference between the 2. Now with cluster autoscaler, right? It takes it a step higher than that. So with the other 2, you're essentially scaling the pods. But then bear in mind that those pods are running on a physical host, and that physical host has its limits, right? So that's where cluster autoscaler comes in. So imagine you horizontal pod autoscaler, you started off with 3 pods on that host, horizontal pod autoscaler eventually helped you to scale to say 10 pods, right? And 10 pods is the limit that host can run. So when a new pod needs to be scheduled, the scheduler is not able to schedule it because we've run out of capacity for that host. That's where cluster autoscaler kicks in. So it helps you to then spin up an additional instance. Now, within the EKS world, cluster autoscaler works with autoscaling groups. So basically, at this point, your EKS cluster is speaking to the API that controls autoscaling groups within AWS. So as you can see here, we have a couple of pending pods here, right? And because the instance is full, right? So we then make a call to cluster autoscaler, right? Which is running. So cluster autoscaler runs as a controller within your cluster, and then it then makes an API call to autoscaling group, and then it will then deploy an additional host. So at this point, when there's a new host in the environment, the scheduler can then deploy these pods that it wasn't able to deploy before. So you see how they are complementary. So essentially, cluster autoscaler is a complement to horizontal pod autoscaling and vertical pod autoscaling. I hope that is clear. Any questions on that?
No.
Okay, awesome. Now we then go. All right, thank you. We then go into Karpenter. So Karpenter is a build up to or an improvement over cluster autoscaler. Right now, with cluster autoscaler, essentially what it's doing for you is it's spinning up new nodes, right? And as we had mentioned earlier, take for example, you're running a managed node group within your EKS cluster, right? A managed node group, essentially underlying a managed node group is an autoscaling group, and if you're familiar with autoscaling groups, you will realize that autoscaling groups essentially run similar instance types. So within an autoscaling group, you want to run, even if you're running, imagine you're running, an M5 instance, right? You want to run similar, maybe M4X large, M3X large, because basically you want them to have similar vCPU counts and similar RAM, right? That's how you're able to effectively work within an autoscaling group. So the instances within an autoscaling group are very, very similar. Now, the challenge from an EKS scaling standpoint with that is when cluster autoscaler, maybe you have three nodes running within your cluster, and horizontal pod autoscaler is scaling because the traffic is increasing. So it's scaling the pods, pod, node 1 is filled up, node 2 is filled up, node 3 is filled up. Cluster autoscaler then needs to, you still need to deploy more pods. Cluster autoscaler then calls the autoscaling group that we need you to provision an additional instance. Now, what the autoscaling group is going to do is going to provision a similar instance as the ones that were there before. So maybe it's another M5 2x large or 6x large, for example, instance that you're going to provision. Now, the challenge with that is you probably just need to maybe it's only maybe 2 or 3 pods that are outstanding, right? But it's going to provision an instance type that you essentially do not need. So imagine you started off your cluster with 3 nodes, right? And that's the minimum number of instances that is running within that autoscaling group, within that managed node group. Now you've scaled up, you need more instances to run, and cluster autoscaler is just spinning up more of the same type of nodes, and you probably don't need that full capacity. So essentially from an AWS standpoint, you are paying for a node that you are not utilizing fully, right? But with Karpenter is an improvement on that, So with Karpenter is able to speak directly to the EC2 APIs. So Karpenter is aware of the different node types that exist within AWS. So it knows that it's aware of M5, it's aware of M6, it's aware of M5 6x large, for example. It's aware of all of those things because it speaks directly to the EC2 API, right? It's also aware of spot instances. It's a way of reserved instances, for example. So with Karpenter, right, instead of just blindly just deploying another M5 X large, because that's what we specified when we created the auto scaling group, Karpenter is able to provision exactly the right instance type that you need to run the number of pods that you have outstanding. So if you just have 2 pods that you need to run, and Kubernetes, Karpenter can see that, okay, to run these 2 pods, I don't need an M5X large. Maybe I need a T3. Maybe a T3 medium is ideal to run that. It will spin up a T3 medium. Do you see the difference here? So with that, we call Karpenter like a just-in-time service. So it deploys exactly what you need to run the nodes or the whole or the pods that you need to run. So it helps you to save time. It helps you to save cost. Now, if you need to deploy 5 additional pods, in real time, maybe because the traffic hitting your cluster is scaling up really fast. A lot of users are, maybe you're running like Prime Day, for example, on Amazon, and there are a lot of users coming in and using that. Karpenter would help you spin up the right instance. So if, for example, immediately you need to spin up like maybe 20 pods, right? And with 20 pods, you probably need maybe a C6 12X large, for example, to run 20 pods. So instead of it deploying with cluster autoscaler, you will probably deploy 5 M5 larges, for example, and that takes time to deploy those, right? But with Karpenter, it will just realize like, okay, 5 of these instances, it might just provision only 1 node that can run all those pods right at the same time. So it's a very intelligent way of scaling your Kubernetes cluster. And Karpenter is an open source service. It's open source, but AWS is the champion of that. But today, to the best of my knowledge, is only supported within AWS. So that is what Karpenter is in a nutshell. Any questions on Karpenter? I'm trying to be mindful of time. I know we have just a minute to go, so I want to quickly run through the last bit. But basically, this is how the architecture of Karpenter works, and it spins up just exactly what you need per time. Now, so security, I'll really breeze through this. What we are trying to look at is what, I don't know if any of you is familiar with what we call the shared responsibility model at AWS. But essentially, the shared responsibility model speaks to what AWS is responsible for and what the customer is responsible for. So that's just what we're trying to do here. We're doing a comparison between the different runtime modes available for EKS. So this is the self-managed worker nodes. The control plane, as we said before, that AWS would always be responsible for that. But everything within the customer end, which is customer data, the images, the scaling of the images and all of that, the customer manages that. You also manage the VPC. With managing node groups, the control plane AWS manages, but the customer is responsible for everything but the OS and the container runtime and the upgrades of that AMI. AWS will do that for you. You see, in contrasting to the self-managed node groups, where that's part of your responsibility as a customer, for managing node groups, AWS takes that part of that responsibility off you and manages that on your behalf. Now, with Fargate, AWS essentially manages the control plane and then manages the AMIs, the OS, the kubelet, and all of that, and also does the worker node scaling on your behalf. And again, like I mentioned before, the worker nodes wouldn't show up within your EC2, your EC2 dashboard, right? Because AWS is managing that on your behalf. But you can run them in your VPC, through a network. I've forgotten the name. You can spin up that network somebody should remind me now. Network interface, in your VPC. So essentially that network interface card or whatever is running within your VPC, and that's the way you are able to access your Fargate nodes that are being managed by AWS on your behalf. So with that, we've come to the end of this introductory session to Kubernetes. I know we started a little late, so we've just crossed the 12 o'clock hour. But I mean, I can stay on for a few extra minutes if there are questions that you have on the session today.
Thanks, Manuel.
Thanks, Manuel, for your presentation. Is there any question, please? Okay, I think everyone understand. Okay, I think everyone understand very well. That's good. Will you share with us, please, the slides?
Yeah, I can do that.
Okay, thanks. I never used Karpenter before. I think after that I will read a little about and see how I can integrate it in my works.
Yeah, I mean it's amazing. It helps you save cost and it helps you save time, because part of the key metrics for us for Karpenter are the ability to spin up those additional instances quickly. So they're actually targets that AWS is pushing in terms of how quickly Karpenter is able to come up. So so speed is one of the very major advantages and benefits you get from Karpenter over a cluster autoscaler. And obviously the fact that you are going to spin up the exact instance type that you need, and you're able to save costs with that. So those are some amazing benefits that Karpenter would immediately give you over a cluster autoscaler.
Okay. With that, some question come in my mind. If, by example, I have provisioned my cluster with Terraform, and I have set in my Terraform module the node type that I wanted, and Karpenter changed that. I will have an inconsistency in my Terraform state, right?
Okay, so this is where I believe GitOps comes in into play, where GitOps would have a state that is trying to align with. So what Karpenter does, is Karpenter comes into play during the scaling portion of or during scaling.
Okay.
Right? Yes. So that's where Karpenter is coming in. You need to scale in real time, and when the traffic patterns when the traffic is reduced, it returns your cluster back to the state that you specified.
Okay.
Does that make sense?
Okay. Makes sense.
Yeah. So Karpenter just comes into play during that period where you have elevated a spike. Exactly. That's where Karpenter comes in and then returns it back. So whatever you've defined, is still the state of your cluster on a normal level, but during the spike, Karpenter then kicks in to ensure that you are able to respond to that traffic and then, take it back to what it used to be.
Okay. Thanks.
You're welcome.
I think if someone, if any other person have a question, we can call it a day. No one. Okay.
I have no question.
but I am coming back.
Okay, let's go.
Okay, Emmanuel first.
She can go on.
Okay,
She can go on.
Lionel.
Oui, en fait, j'essaie de traduire la question d'abord.
You can speak French. I will translate for you. There is no problem.
Ok, d'accord, merci. Donc, en fait, ce que je voulais dire, c'est, étant donné que Karpenter n'est pas un service directement lié à AWS, c'est-à-dire pas un service officiel à AWS, est-ce que c'est vraiment prudent d'utiliser directement comme ça, alors que nous avons déjà des services AWS qui font exactement la même chose que lui?
D'accord.
C'est ce que j'ai compris de sa présentation.
Okay. Lionel said that since Karpenter is not a direct service of AWS, is it safe to use that? Is it safe to use that? And he think that also there is another service in AWS that do the same thing as Karpenter. So that is the question.
Okay, so first of all, Karpenter was developed by AWS, right? As an open source project, you know. So that's the first thing that I would say on that. The second thing is that I mean, with part of the beauty and the flexibility of Kubernetes is the ability to bring in add-ons, right? So you have a lot of add-ons that you can bring into Kubernetes. You know, if you want to run observability, for example, you can bring in add-ons like FluentBeat, FluentD. You want to expose stuff like Grafana. You know, so there are a lot of third-party services that naturally today you're able to bring into your Kubernetes cluster. I also spoke about during the presentation, if you want to expose your cluster, your workloads running on Kubernetes via third-party services like what do you call it, Nginx, for example, you know, you're going to have to install an Nginx controller inside your cluster, right? So that's where your responsibility comes in as the administrator of your cluster, to be sure that, okay, you know what exactly you're bringing into your cluster, you know, and that you're working within the appropriate guidelines. But to make your cluster, Kubernetes cluster, you know, deliver on what you want it to deliver, you would definitely leverage third-party services. But the point I'm making is, within this case, you know, Karpenter is developed by AWS, even though as an open source project. Now, to the second part of the question, that AWS has a service that does this. Within the Kubernetes and EKS world, no, we don't, right? But what you also need to bear in mind is that Karpenter is not doing anything out of the ordinary. You know, it's speaking to the EC2 APIs. The EC2 API already exists today, you know. So Karpenter is just the link between your EKS cluster and the EC2 API. So that's how you want to think about Karpenter. You know, so it's just leveraging what already exists to be able to deliver value to your Kubernetes cluster. I hope that makes sense.
Okay, thank you.
To add something to his question, Lionel, we can also limit the right of the service used by us, the service account used by Karpenter. So if we want, by example, Karpenter not being able to provide on some kind of EC2 instance type, we can limit the access given to him.
Yes.
Okay, d'accord.
Correct.
Okay. Thank you.
Correct.
So, any other question, Emmanuel?
No question. I would just say thanks to Mariwa for sharing his knowledge with us.
You're welcome. You're welcome. Thanks for being a good audience as well.
Okay. Thank everyone. Thank Mayura. I will send the link of the record. I will publish it on our YouTube channel and send it to you, and also publish it to LinkedIn so people can catch up.
That's fine.
Okay. Thank you. Thank everyone. Goodbye.
Thank you, everyone.
Okay,
Bye.
see you next time.
Bye.